All right, guys, today we got the multiplication rule. Yesterday we did the addition rule, so this is a tad bit different, but still probability. All right, today we're going to be finding the probability of A and B. Remember, yesterday was A or B. Today's A and B, and that's how you know the difference of when you multiply, when you add. Whenever you see the word and, I want you to think, oh, it means multiply. So probability of A and B is the probability that A occurs in the first trial and B occurs in the second trial. Now, one other notation, I tried to write this on here. There's supposed to be a bar between there. When you see that bar between B and A, it means the probability of B occurring after it is assumed that A has already occurred. And sometimes after A has occurred, it does change B. So when you see that bar there, probability of B after A has occurred, that's what that means. The formal rule looks like this. Probability of A and B is always probability of A times probability of B given that A has already occurred. And I wrote it in a sentence form here. I'm just going to read that. Sorry about that. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event B takes into account the previous occurrence of event A. That's a mouthful, but it's the same thing I've said about 3 times. When you have 2 events that are going to occur, one first and then the other one, make sure before you do probability of your second one and before you multiply, you do take into account that the first one has occurred and see if that changed your second probability at all. All right, a few more words here. Independent. Independent means the occurrence of one event does not affect the probability of the other. Dependent means they're not independent, which means one event does affect the probability. Not that they affect each other, but one affects the probability of the other. Big word of caution. Don't think that dependence of 2 events means that one is a direct cause of another. They don't cause each other. Having a working TV in your room and having working lights are dependent because they have the same power source, even though neither one has a direct effect on each other. So we're more interested in the effect, not if they're coming from the same source. Sampling with replacement, these are big words too. Sampling, of course, is always important, but with replacement means they're independent. Without replacement means they are dependent, and you have to worry about this. When it's dependent, that's when you have to worry about the B, given that A has occurred. That's going to be a big deal there. And another humongous thing here, treating dependent events as independent. We are going to do that sometimes. We're going to have a 5% guideline, just like we do with everything else, for cumbersome calculations. When calculations with sampling are very cumbersome and the sample size is no more than 5% of the population, so if you have a small sample size from a huge population, we're going to act like they're independent even if they are dependent. Okay, I'm going to show you about 3 or 4 examples and we'll be done. This first one, same old chart here. You've seen this one a lot now. If 2 of the 50 subjects are normally selected with replacement, now I'm talking about the 50 who tested the used drug. So all we're looking at is that row right here, these two, that row. With replacement, find the probability that the first person selected had a positive result and the second person had a negative result. Now, the first person having a positive result would be 2, well, there's 44 people who had positive out of 50, so we would say it'd be 44 out of 50 times. Now, because we're replacing, even though we picked that first person, we're putting them right back in the hat, and it says in the second person had a negative. Well, that means there's still 6 that had a negative, and we just multiply that out on the calculator and we get 0.106. Now look at part B to see the difference. What if the second selected person was selected without replacement? So the first person is still the same, all right? 44 to 50 chance of getting someone with a positive test. Now the second person with a negative test, here's the deal. There's still 6 people in there who've had a negative test, but there are only 49 people left in the group because I already picked one who had a positive test. So that's what happens. That's dependent. And if you multiply that one out, you get 0.108. So a little bit different there. So be careful whether it says with replacement or without replacement. Another example, airport baggage scales can show that bags are overweight and high additional fees can be imposed. The New York City Department of Consumer Affairs checked all 810 scales at JFK and LaGuardia, and 102 scales were found to be defective and ordered out of use. If 2 of the 810 scales are randomly selected with replacement, find the probability that they're both defective. Now, we're going to replace it, so you have a 102 out of 810 chance of picking the first one that's defective. And because you're putting it right back in the hat, you have a 102 over 810 chance again of getting one that's defective. So if you multiply those, you get 0.0159. Now, part B, if 2 of the 810 scales are selected without replacement. Okay, so the first one, you still have the same probability, but the second one, now that you've picked one, there's just 101 left in the hat that has is defective, and there's only 809 left in there. So you see how it decreases when it becomes dependent. So 0.0157 instead of 9. And the last part here, part C. A larger population, hint, hint, of 10,000 scales includes exactly 1,259 defective scales. If 5 scales are randomly selected, now 5 is a whole lot less than 5% of 10,000, so we're going to act like this is dependent. It says without replacement. So even though it says without replacement, we're going to act like it said replacement because the sample is so small compared to the population. So the first one, we would have a 1,259 out of 10,000 chance. And the second one, because we're going to act like we're replacing it, it's going to be the same thing. And because the third one, because we're replacing it or we're acting like we're replacing it, it's going to be the same thing. The fourth one basically is going to be that right there to the 5th power. I guess I should just shorten and say it's going to be that to the 5th power. Punch it in your calculator. It's going to be so stinking small. It's 0.0000316. Remember, 3 sig digs with probability. All right, so hope this is starting to make a little bit of sense to you, the difference in the independent and the dependent. All right, caution. It is extremely important to carefully identify the event being considered. Some things are similar, but their solutions are very different. So I'm about to show you what I mean by that with this example right here. It says when 2 different people are randomly selected from those in your class, find the indicated probability by assuming that birthdays occur on the days of the week with equal frequency, meaning there's an equal number of people born on a Sunday or Monday or Tuesday. The day doesn't matter if there's an equal chance of that happening. Not, the Sunday is not more popular for having a baby. So, part A, find the probability that 2 people are born on the same day of the week, which means, let's say I find the first person and they say, oh, I was born on Wednesday. Okay, what are the chances that the next person was also born on Wednesday? Well, 1 out of 7, and that's all you do. But look at part B. Find the probability that the 2 people are both born on Monday. Okay, now we're talking about both people picking a specific day, which is different. The first person has a 1 out of 7 chance of being born on a Monday, and the second person I ask also has a 1 out of 7 chance, so they have a 1 out of 49 chance of being born on a Monday. And that's an and, even though I didn't say the word and, think about it. The first person and the second person were born on Monday. All right, a couple more here. Microsoft's XSort gender selection technique is designed to increase the likelihood that a baby will be a girl. Look at part A. Assume that in a preliminary test of the XSort technique, 20 couples give birth to 20 babies, and all 20 babies were girl. If we were to assume that XSort method has no effect, what is the probability of getting 20 girls and 20 births by random chance? Okay, so every time you have a birth, the chance of having girls is 1/2. So the first one, the second one, the third one, they're all 1/2. I could write out 1/2 20 times, but bottom line is they're all 1/2. So what I'm going to do with my calculators, I'm just going to punch in 0.5, which is 1/2, to the 20th power. And when I do that, this is what comes up. I get 1, 2, 3, 4, 5, 6 zeros, then my 3 sig digs, 9, 5, 4. So the chances of that happening by chance is extremely low. So it says, what does that result suggest? Well, it suggests that random chance is not a very good explanation. The better explanation is that the technique actually works. Let's go to part B. Part B says, here are the actual results from the gender selection technique. Among 945 babies born, 879 were girls based on the data. The probability of these results occurring by random chance has no effect from the XSort method. It would be calculated to be what we call 0 plus. If you see a 0 with a plus sign, here's what that means. It denotes a positive probability that is so close to 0, we consider it to be 0 for all practical purposes. So, does a probability of 0 plus provide strong evidence to support a claim that the method is effective? Yes, because it is so much lower than, like, our standard is usually 0.05, and that's basically 0. So because that is so small, the chances of that happening, this number out of that number, by just random chance is almost, basically it's impossible. So their technique definitely is effective. Last one, I promise. Modern aircraft are now highly reliable, and one design feature, thank goodness they are, and one design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if any one system fails, full flight control is maintained with another functioning system. For this example, we assume that for a typical flight, the probability of failure for a hydraulic system is 0.002. Okay, if the Airbus were to have one hydraulic system, and we already know it has 3, what is the probability that it would work for a flight? Well, this is the probability of failure, so the probability of success is the complement of that, which would be 0.998. So it's very high that it's going to work for the flight, thank goodness. Okay, given that the Airbus 310 has 3 hydraulic systems, what is the probability on a typical flight control could be maintained with a working hydraulic system? Okay, so that's the chance of failure for the first one, and this is the probability for failure for the second one, and that's the probability for failure on the third one. So the probability that all 3 of them were to fail would be, oh my gosh, 1, 2, 3, 4, 5, 6, 7, 8 zeros with an 8 at the end. So what that means is, this said, what's the probability that can be maintained with a working one? Well, that's the probability that all 3 fail. So the probability that at least one is going to work would be 1 minus all of that stuff right there, which would give me 0.999999992. All right, so it's going to work. That's almost 100%, or almost probability of 1. So I'm glad they do that. It's a great idea, and look how effective it is. Hope that made some sense to you. A lot of stuff in that section, and we'll talk about it tomorrow and work on some problems. See you then.